Hello engineers, welcome back. In this video, we're going to continue with our discussion on core concepts in system design and we're going to discuss data flow. I hope you're ready. Let's get started. So we'll first start with the question, what is data flow? To understand what is data flow, we need to understand what is the difference between data in motion versus data at rest. So to understand this, let's look at a lake. So when there is a water body such as a lake, the lake is not going anywhere, right? And there is always some water in it, there are some animals in it, there are some fishes, plants growing inside it and so on. But the lake itself is not going anywhere. This is similar to what we describe as data at rest, right? Some of the examples are, let's say, a database server or maybe a disk or maybe even a data lake like this. So this is where data is persisting. There are mechanisms to keep the data in place and the data is not going anywhere. The main concerns here when the data is at rest is mainly about security, to make sure that nobody that is not authorized is able to access this. So the main concern is security and also encryption. So just in case somebody gets their hands on it, they should not be able to open it or access the data inside it. Right? So these are the main two concerns, security and encryption. So this is what data at rest looks like. Now let's see what data at motion looks like. So think of it as a river. So if there is a river body, the water is always flowing. The river is always connecting to some sea or ocean, right? So the data is always flowing. So what is the example of this? Let's say we are uploading some file to some server, right? And the file is going in some chunks. So while it is traveling, the data is said to be in motion. Another example could be an IoT sensor, let's say. An IoT sensor is sending its current updates like its battery life or something that it is measuring to a nearby service and it is continuously streaming that data. So this again is data in motion, right? And another example could be computer nodes connected with each other, maybe microservices or some services talking to each other. And during this transition phase, the data is said to be in motion. Maybe the data needs to travel to all of them before it can complete its operation. That is when we say that data is in motion. And the main concern here is TLS, transport layer security basically. And we are really worried about who is sniffing the data while it is in transit, right? And we don't want to give away any information that we want to. And that is the main concern here when the data is in motion, right? So that is what data flow means. Now let's try to understand why we need to flow the data in the first place, right? Apart from the general reasons like sending out messages, receiving messages and files and so on, the main reason why we want to flow data to different systems, especially in the case of distributed systems, is to achieve these things. The first in the list is scalability. We want to achieve high throughput. We want our services to be able to handle high traffic. And because of this, we will give responsibilities to different systems. For example, if entire traffic is going through this river, the river may overflow. But if we create canals like this, which will take care of its own thing, and another canal which will take care of its own thing, we can actually contain the flow of data or control the flow of data so that we can achieve high traffic and high scale, right? Another thing is reliability. We want our data flow to be able to handle crashes. And maybe some data is in transit and the service has crashed. We want to be able to restore or resume from that spot. So all these things are taken into consideration whenever there is data flow involved, right? Another thing is performance. If one of the services is stuck, we don't want the entire data flow to be stuck. We want to keep things as async as possible. And because of this, we can achieve more performance, right? Nobody is waiting for anybody else. They are all doing their own things. And whenever they are ready, we will process the next step and so on, right? So these are some of the advantages of flowing data. Now let's try to understand the three different patterns or three different styles of data flow and see their features and what they have to offer, right? So let's go to the first one, which is message queue. So what is a message queue? To understand message queue, we can simply take the example of a post office. So let's say somebody wants to send a post. So they drop it at the nearby post box or the nearby post office, and it is the responsibility of the post office to process this post or this message, right? So the post office will take a look at its address and see where it's supposed to go. It routes it through the internal channels and finally it will reach the destination and the mail is finally delivered, right? So this is how post office works. Similarly, in the case of computer systems, there are producers who are actually sending out messages and there is some kind of a post office which is called a message queue broker or a message queue system, which is taking care of processing that message and sending it to the appropriate consumer, right? and then this consumer can do whatever they want to do with it. And this is how a typical message queue system works. So in this case, as long as there is no post, there is no job for the server. So as long as there are no incoming posts, there is no job for the post office, right? So this means that this is mainly a event-driven system. So whenever there is a message or whenever there is some event that has happened and somebody needs to be aware of this, we send out a message and that message needs to be processed by some consumer, right? So this is the high level idea about what message queues look like. But if we take a look at it closely, let's open this message broker up and see what happens here. So let's say there are multiple producers. There can be different producers. Maybe it's a mobile phone that is producing it. Maybe it's a desktop. Maybe it's my watch. Maybe it's some other server or some other internal service, some other IoT sensor. Anybody can be a producer that is taking care of producing an event, creating that post, right? And they send it to some kind of an exchange, right? So this message broker system carries an exchange where it will sort out the messages and send it to different things. So what happens here is there are different queues and consumers are listening on those queues. So they're basically listening on queues. So they could be listening on all the queues, they could be listening on some specific queues. Depending on that, they will consume it whenever there is a new message. Let's say this consumer is listening on this queue, and if some message is pushed here, this consumer can pick it up and then process it, right? And do whatever it wants to do with it, right? So this is how message broking works. So there's an exchange system that takes in all the incoming messages and puts them in the respective queues. So there could be different strategies for achieving this spreading of messages. One of the options could be a fan out, another could be topic based. So if it's a fan out, let's say every message needs to go to every queue and every consumer needs to be aware of it. We can make use of this concept. Otherwise, we can be specific about what topic we want to do. Let's say we have ordered something on Amazon and that order status needs to be delivered to the consumer, right? Let's say order is out for delivery. This is my message. And some system, internal order processing system, has given out like a producer that, hey, order is out for delivery. And this message comes here and it only goes to the queue that processes out of delivery messages. So this is like a specific topic. Let's say this goes here, OFD, out for delivery. And whoever is processing this consumer, they will take care of this message and send out the push notification or the email or whatever needs to be done for that particular message, right? So this is how typically message queue systems work. They're mainly event driven. Now let's see some of the advantages of using a message queue. First thing is decoupling. So the producers and consumers don't need to know about each other. That is one of the main advantages. They can keep doing their own things. They're not even aware of each other. So the producer producing the message is not aware of who is going to actually consume and process it. It is like fire and forget, right? So that is one of the advantages. And second thing is we can get asynchronous operations here, because producer, after sending the message, need not wait for the consumer to consume it and process it. Producer can continue to do its own thing, right? So we can get asynchronous behavior here. And we could also achieve load balancing here by creating multiple nodes of message queues, and they can distribute the traffic among themselves so that no single node is heavily loaded. And we can also achieve fault tolerance. In case the node crashes, it has some mechanism to keep the message persisted within itself so that when it is back up, it can still continue to send out that message, and we achieve some kind of reliability and fault tolerance here, right? Now let's see some of the features of message queue systems. So first thing is delivery guarantees, and there are three ways to achieve this. First one is at most once. It means that it will just fire and forget. Okay, so the responsibility of the message queue system is just to send out that there is some message, and it is not bothered whether there is some consumer available or whether anybody is processing it or not. And the second one is at least one. So here we are waiting for the acknowledgement from the consumers. So at least one of the consumers should acknowledge that, hey, I've received it, I've processed it, now it is safe to be dismissed. And the third one is exactly once. So this is a very tricky one, because to achieve exactly once, at least one of these are getting violated. So for example, if the message queue is sending a message to, let's say, some consumer, and consumer has processed it, but while it is acknowledging, there is some network crash, right? And because of this, message queue is never aware that consumer has received it or processed it. So it is waiting and waiting and waiting. And let's say there is some threshold hit and it is sending out to some other consumer the same message, right? And because of this, we have violated this one at most once. And because of this, the same message is processed by two different consumers, and this causes duplication, right? And this is an issue with going for exactly once. So this is a hard problem to solve, and some message queues don't even guarantee this. But it is an interesting case to look at if you are interested in doing some research in this topic, right? So definitely check out this one if you are further interested. And another feature of message queue systems is persistence. Like I said, in case of any system failure, the messages are persisted, and when it's back up online, it can be processed further. And we also get the option of dead letter queues. So let's say some messages are never processed, no consumer is able to pick it up, or maybe nobody has acknowledged them, or whatever may be the case. We need to know that some messages were not processed. So it holds an area especially for this type of messages where we can see or debug or analyze what is the problem and take it from there, right? So these are some of the features of message queues. And there are a couple of patterns. One is point to point, which means that there's a direct link between producer and consumer, and this is point to point. And if it's a publisher subscriber system, producers are producing it to some exchange and consumers are listening on this exchange. So there can be multiple consumers listening on maybe different sets of topics, and they will be able to consume the messages from the exchange, right? So this is the famous publisher subscriber model or PubSub model. So some of the popular tools for doing message queues is RabbitMQ, Amazon SQS, which is simple queue system, and also Apache Kafka, of course. So this is all about message queue systems. Now let's go into the second type of data flow, which is batch processing, right? So for batch processing, think of it like doing your laundry, right? Let's say this is a washing machine and we are dealing with some clothes, right? And washing machine can only take a certain amount of load at a time, right? And when it is taking this load, it is very effective with that load. So we get a load, we dump it into the washing machine, and the washing machine does its job, and until it finishes, we cannot give it new load, right? Because there is no space in the washing machine. And similarly, we can just pile up our batches like this, which are ready to go once this batch is finished, right? So this is how batch processing works. So there is a large load of data being processed at a time, and only that load is processed. So with this, I hope you are able to visualize the concept of batch processing, right? So in the computer world, so let's say there are multiple data sources that are pushing out data. So this data is not processed immediately. They are collected in batches and they are kept in the batch processing system. And when it is time to process them, one of the batch gets picked and it is processed, and it gives out a certain output again in batches. This batch gives out a certain output, which is the output for this particular batch, right? And this batch processing can take from minutes to hours depending on the complexity of the batch processing. And this is how batch processing typically works. So there is an incoming flow of data, and then they're collected in batches, they're processed at a set interval or set time, and one batch will produce some kind of an output, right? Now let's see why we need to do batch processing. So these are some of the use cases, popular use cases for batch processing. Maybe we want to do a monthly payroll, which is a large chunk of data that is processed once a month, let's say. And this is a very good example of a batch process. And maybe we want to do end of day reports. We want to collect some kind of reports of the activities performed during the day. And for this, we need the data for the entire day to be collected. And at the end of the day, maybe at midnight, we run some kind of number crunching or some kind of algorithm for the data collected during the day. And then we send out some reports, right? And any ETL system, ETL stands for extract, transform, and load. So any ETL system, maybe there is some kind of a data that is being collected, transformed into some other format, and then loaded into some other data warehouse or data BigQuery system or anything like that, where further processing is required, we can make use of batch processing. Again, the idea is simple: collect the data in batches, process them one batch at a time, and then do something with it, right? Now let's see some of the features for batch processing systems. We get high throughput, which means that we are able to process large amount of data in one batch. So we are getting high throughput here. And we also have high latency, which means that every batch will take its own sweet time to process. Like we have seen in the example before, it could take from minutes to hours, right? Depending on the complexity of the batch or depending on the complexity of the algorithm that is processing the batch, right? And because of this, we also get resource efficiency because we are able to schedule it at a particular time, at a convenient time that is suitable to us, maybe at midnight when everybody is sleeping, maybe when the resources are available fully for batch processing, and so on. So these are some of the advantages or features of batch processing. So the workflow of batch processing involves 3 steps. First is the ingestion phase. We need to take care of ingesting the data in the correct format for the processor to be able to process. So this is what is called as ingestion, the incoming data. And then there is processing, which is the actual algorithm or analytics that is being run on the particular batch, right? And then there is the output phase. Output can be a simple file or an email, or it could be a load into another system where further processing can happen, right? So this is how the workflow is designed for different use cases of different batches. So some of the popular tools are Hadoop, Flink, and Kafka from Apache, and almost every cloud provider has some kind of a batch processing system. Maybe you can look at Google Cloud Batch and so on, right? So this is all about batch processing. Now let's look at the third one, which is stream processing. So for stream processing, we have already seen this before. We can think of it as a river of data, right? Which means that the data needs to be processed in real time. So let's say there is a flow of data. So each data point is picked and processed in real time. So that is the idea behind stream processing. So we are not talking about the real-time streaming of videos, let's say for a football match. We are talking about a complex backend system that is getting incoming flow of data and it is doing something with it. So in the computer world, this is how it looks like. So there can be multiple producers of the data, which are producing continuously some kind of operation or some kind of data, and the data is being sent to some kind of a data stream, right? And the data stream is like a queue. Data is coming from one side and going out the other side, and every bit that is coming out of the data stream queue is being processed by the stream processor, and this processor is responsible for doing something with it at real instant time, and then it sends out the output again in streams, because every bit of data will have some kind of an output. So the data output is also a stream, and the data is coming in a queue format, and then this data stream is being consumed by somebody else. Maybe we are giving out live score updates, and that can be one of the examples. And maybe we are showing some data on some public dashboard. We can use that here, or maybe we are pushing it to some database, and maybe we are pushing it to some data lake for further processing, and so on. So it depends on the nature of the operation, but the idea is to send continuous streams of data, and the data is processed in real instant time, right? Now let's see where we can see these streams. So these are some of the popular use cases. So if we want to do real-time recommendations, so we want to give out recommendations based on the current activity of the user, let's say. Now let's say I'm on some kind of e-commerce platform and I'm searching for football t-shirts, let's say, and the system immediately gives me suggestions from different football teams and different players, and this is happening in real time, right? So my session is being observed, the clicks that I'm making, the kind of time I'm spending on different items is all input to an analytics system which is giving out recommendations, right? Another example can be live dashboards. Let's say I'm on some kind of a sports app like CrickBuzz or something, where I'm continuously monitoring for commentary and score updates, right? So there is some other system taking in the live updates from official cricketing sources and then pushing that data to me. So this is happening in real time for every ball or every minute. Or maybe I'm monitoring a large data center with hundreds of servers, and I'm monitoring the health of these servers. So every server is sending out its health update to a certain central mechanism, and that central server is responsible for putting it on the live dashboard, and it is showcasing the health of different servers, and I'm able to monitor it. This is another use case of using streams. And another use case can be with IoT sensors. They're continuously sending out health checks of different machines they are on, and if there is any anomaly or any failure detected, we can be immediately alerted, right? So these are some of the use cases of using stream data. Now let's look at some of the features or concepts that are used in stream processing, right? The first one is event time versus processing time. So the time when the event has happened is called event time, and the time that is taken for the stream processor to process that particular data object or data item is called processing time. So depending on the need or the question that we are asking, we can use either of those times. For example, if you want to get the average of, let's say, number of clicks I made in a browser, I will be using event time. I will not be using processing time, and so on, right? So there's a difference between event time and processing time. And there are also windows involved here because it is a continuous stream of data. We need some kind of a boundary to decide or do some analytics with it, right? So the first example is tumbling windows. So these are non-overlapping, not overlapping, which means that one window is not aware of the other window's data. For example, daily updates. So let's say we are talking about sales per day. So one day's sales will never overlap with the second day's sales, right? So this data is independent and this data is independent. So if you're talking about analytics that involve non-overlapping data, we are looking at tumbling windows. The second one is sliding windows, which are the opposite, which are overlapping data. So for example, we are talking about moving average. Let's say I want to look at the share price of some stock for the last 20 minutes, right? And this 20 minutes keeps on changing every minute, right? So the last 20 minutes is decided based on current time. And the first window, which are 20 minutes, will have 19 such data points with the next window, overlapping data points. And this is how moving average works. So there is continuous overlap and one data point is getting removed and one data point is getting added and so on, right? So this is how moving averages work. And the third one is session based. So this is not based on any particular time window. This is based on some kind of a start time and end time. So I'm on a browser, I've started my session, I've logged in, and until I log out, let's say that is my session window. So we're talking about session windows in that fashion. So these are the different windows that are processed in stream processing. And then we can also have state management. So if you want to remember past streams, let's say I'm doing some kind of a counter, right? Let's say I'm counting the number of clicks I'm making in a particular session. So every data point is giving me some clicked. And I need some kind of a universal counter or a tracker that is keeping track of clicks coming from all the data stream points, right? So stream processing also gives us some kind of state management so that we can keep a track of some things. We can do some aggregation and things like that. And the last feature is watermarks. Think of it like the baggage claim at the airport. So watermarks are used for deciding the end of a stream, right? So I'm waiting for my baggage at the airport and there is a continuous stream of bags coming out through the belt, right? And my bag hasn't come yet. So I'm continuously waiting and I don't know whether all the bags from my aircraft have been put on the belt, right? How will I know that? So there is some kind of a TV or some kind of a display where it says first bag on the belt or last bag on the belt. So based on this particular information, I can know that, okay, the last bag has been placed on the belt, but I still don't find my bag. That is when I can decide that, okay, the stream has ended. Now I can go make a complaint that, hey, everybody's bags are received, but my bag is missing, right? So the watermarks are like the endpoints of a stream. So these are some of the features of the stream processing system. So again, some of the popular tools are Apache Kafka, Amazon Kinesis, Google Cloud's Dataflow, and so on. So there can be more examples like this, but you will notice that Kafka is everywhere. It is there as part of stream processing, batch processing, and also as part of our pub sub system. So Apache Kafka is like the superstar of all these systems, and it is very powerful and quite feature rich. So having discussed all this, I would like to leave you with some homework and let me know in the comments below. We have talked about distributed systems a lot throughout this playlist, and I've deliberately left out the challenges with the data flow systems. So I would like you to research on it and let me know in the comment below what are the challenges that can be faced in distributed systems when it comes to the usage of either stream processing or batch processing or message queues. So that's the homework for you. Let me know in the comment below. That's all I had for this video, guys. Do leave a like if you found this helpful. Please subscribe if you haven't done already. Thank you so much for watching. I will see you in the next one. Cheers.